Let's find the linearization of f of x equal to 6 plus 1 over x to the 1/3 power at a equal to 1. This problem isn't as bad as it looks. All they're really asking us to do is find the equation of the tangent line. So we have to do essentially two things here. We have to find the derivative. So let's do that first, actually, since they've already been told the function. So our derivative here is going to be, let's say I got some stuff to the 1/3 power. It's going to be 1/3 times my stuff to the negative 2/3 times the derivative of that stuff. It might be more helpful to think of this stuff as 6 plus x to the negative 1, so that the derivative is going to be 0 plus negative x to the negative 2, or just negative x to the negative 2. And then we essentially have to remember the linearization formula, or remember the fact that we're doing the equation of a tangent line. So we have, I guess we could find the slope and the point. So the slope is going to be f prime of what? What am I plugging in to actually find the slope? Show me on your fingers. Exactly, yes, 1, right? Because they told us over here, oh yeah, we're doing this at a equals 1. So f prime of 1, we're just going to plug in 1. I actually wouldn't simplify this. I would just plug in 1. I wonder why they picked 1's a terrible number for this problem. Who picked 1? That's an awful. I do not love this. So usually the point of a linear. So now I grabbed this problem from web work. Usually the point of linearization is you're making it like nicer to calculate. 1 is not excellent here. Let's see why. So if I plug in 1, I'm going to get 1/3 times 6 plus 1, which is 7 to the negative 2/3 times negative 1 to the negative second. Okay, is negative 1 to the negative second negative 1 or positive 1? It's negative 1 because the power is happening before the negative sign. The reason I'm annoyed by this is because 7 to the negative 2/3 is not nice. It's just going to be 7 to the negative 2/3. It should have been 8. So it was 8, then it would come out 8 to the negative 2/3 is like 1/4. So somebody did a not great job of picking a number here. Yeah, that's kind of a bummer. In fact, let's change the problem. Let's make it a nicer problem. So instead of this problem, we're going to say, let's cross this out. Well, let's change it to, instead of a equal to 1, let's make it a equal to 1/2. And somehow I've frozen up here. Interesting. That is real interesting. What is going on? Yes, we're having some computer issues over here. They had to replace the computer, so I'm not exactly sure what's happened here. We'll try to get back on track in a second. Apologies. So you all try plugging in 1/2 for x while I try to fix this. So do f prime of 1/2. You're going to get 1/3 times 6 plus 1 over 1/2 times negative parentheses 1/2 to the negative second. It's going to be a much nicer value once we actually simplify it, assuming this ever does anything here. Let's try that again. We'll open it back up. Is it on? It's on. Is it plugged in? It sure seems to be. Okay. Oh, it did something. All right, let's try again. Should be connected. It's really good. You got give that a shot while I work on fixing this. You can plug that in. You can do the math. Oh, there it was. It just came back up. There we go. All right. Back in business. Be very gentle with, oh my God. Okay, I feel like I can't touch anything over here, so I'll just try to move my paper around so it's in the right spot. Okay, so making this problem more interesting, plugging in 1/2 instead of 1. Let's see what we get. So our slope here is going to be f prime of 1/2, which is going to be 1/3 times 6 plus, let's be smart here. I don't want to write 1/1/2. 1/1/2 is 2 to the negative 2/3 times negative 1/2 to the negative second. We should definitely simplify this. So here's how this is going to simplify. Got a 1/3 out front. This part here is 8 to the negative 2/3. 8 to the 1/3 is 2. 2 to the negative 2 is 1/4. And I think we're going to get the same thing here, in fact. 1/2, oh no, it's going to be the opposite of that. Because 1/2 to the negative 2 is going to be 2 squared, which is 4. So that's going to be a negative 4. So we have a 1/3 times a 1/4 times a negative 4. The 4s will cancel and we'll get a negative 1/3. I should be writing these problems. It's much better than what they had. Yeah, it's really, it's terrible. So then we've got our slope. We still need a point, an xy coordinate. So we know that if a is 1/2, f of a, so our a comma f of a is going to be our point. And that's going to be, let's see, well, that's a is 1/2. And f of 1/2 is going to be 6 plus 2 to the 1/3 power. And that's 8 to the 1/3, which is in fact 2. So that's our f of a. So if you want to think of it this way, you could then go find the equation of your tangent line. You could say y minus the y coordinate equals your slope times x minus the x coordinate. So one way to do this, although not the kind of standard way for linearization, would be to say, great, y minus 2 equals my slope, negative 1/3, times x minus 1/2. And then we would add the 2 to both sides. The more typical way of remembering this is to think of it as the linearization is equal to f of a plus f prime of a times x minus a, and then just jam everything we just found. So that here your linearization is f of a, which is 2, plus f prime of a, which is negative 1/3, times x minus a, which is x minus 1/2. But I really just wanted to remind you all, the linearization is really, really, really just the equation of the tangent line. Questions about this before we look at one more linearization example? Yeah. All right, let's go one more. So this is, if it were up to me, this is the kind of question that someone would ask you on your test. Use a linearization to estimate or approximate, sure, 2.9 to the 3rd power. Oops, you can't see that, sorry. So here, they didn't tell us what the function was. They didn't tell us what the a value was. It's kind of up to us to figure that out. So first things first, the function f of x, you're basically going to take this and replace the number that seems like it should be having a different value anyway. So I really don't want a 2.9 there. I want an x there. So our function should be x to the 3rd. And instead of plugging in 2.9, we're going to plug in a nicer value. What's a nicer value that's close to 2.9? 3. So that's going to be our a value. Our a is our nice value, which in this case is 3. We should also find the derivative. So our f prime of x is going to be, I do not, don't love these numbers for reasons you will see. The derivative is 3x squared. Yeah, it's dumb. Oh well, such is life. Sometimes the examples are dumb. So then here's why I don't like this example. Our f of a is going to be 3 cubed, which is 27. And our f prime of a is going to be 3 times 3 squared, which is also 27. I don't like it because I would rather those were just different so we could see the difference between them more easily. But oh well. So then linearization. L of x is f of a plus f prime of a times x minus a. That's going to be 27 plus 27 times x minus 3. So that's the linearization. But then we have to actually use it to do the thing they asked us to do. They said, great, estimate 2.9 cubed. Well, this is an approximation of our function. So what we really should be saying here is that f of x is approximately this. So then if I want to find out what f of 2.9 is, right, f of 2.9 would actually be 2.9 cubed, but it's approximately equal to the linearization evaluated at 2.9. And then we just plug in 2.9 for x and we get 27 plus 27 times 2.9 minus 3. And then we simplify it. That's going to be 27 plus 27 times negative 0.1, which is really just 27 minus 2.7, which is what, 24.3? That's the idea here. Yeah, they're usually not too terrible as far as questions you might see on the exam about linearizations. All right. Let's move along and talk about essentially all the ins and outs of graphing. Because that's really what all this increasing, decreasing, relative maximum, relative minimum, concavity, inflection points, all that is really in the guise of drawing a nicer graph. Really. So let's start off with some, we should say one other thing first. So let's start off with something else first. So before we get there, there's one other thing we should mention. Whoops, sorry. So, yeah. So there's relative extrema, which are also called local extrema. For example, this function, f of x equal to, where'd you go? I had an example over here. There we are. Yes. F of x equal to, I don't love that one. So let's do this one. X cubed minus 3x squared. This function has some local extrema, which I'm just gonna graph it and then we'll talk about, we'll go back and actually graph it together. But I'll just point out for now, this graph looks like this. It bounces off the x-axis right there at 0, 0. It's also got a point here at 4 comma, sorry, not 4, apologies, 2 comma negative 4. This point here is a relative minimum. Because it's lower than all the points next to it. It's not an absolute minimum though, because the graph definitely gets lower than it as you go way over here. Similarly, that point right there is a relative maximum. Again, for the same sort of reason, that point there is higher above than all the points immediately next to it, or relative to it, or local to it. This graph also does not have an absolute maximum because again, over here to the right, it just keeps getting bigger and bigger and bigger. What else do I want to say about that? Not a whole lot, really. We'll backtrack here in a minute to talk about how we find these things, but I just wanted to kind of point that out. Whereas my favorite, one of my favorites, this function, g of x equal to x squared, which I know you all know how to graph. It's your usual parabola. Something like that. That point right there is both a relative minimum, because yes, it is smaller than all the points immediately next to it. It's also an absolute minimum, because it is the smallest point on the entire graph. The lowest, I should say lowest, that's a better word. The lowest point on the entire graph. Let's do one more. So I'm going to give you one more example on this page here. Let's look at h of x equal to, yeah, let's make it real simple. Let's make it 2x plus 3 on the interval from 0 to 4. So check this out. If we graph this, it's going to be just a piece of a graph. If I plug in 0, I get 0 plus 3, which is 3. If I plug in 4, I get 8 plus 3, which is 11. So it's not going to look perfect. That's totally fine. It's a straight line from there to there. So this graph does not have any relative extrema. I'm going to say that again. This graph does not have a local maximum. It does not have a local minimum. Because technically, if you look in the book, it gets they're kind of a little hand wavy about it. But if you read carefully in the textbook, and your professor also should have said this, to be a relative maximum or minimum, it has to be bigger than or smaller than all the things on both sides of it. Meaning it has to be defined on both sides. And if it's not, you can't call it a relative or local maximum or minimum. So these two things here, we don't call them relative extrema, but they are absolute extrema, right? Certainly on this graph, that is the absolute lowest point. So this is for sure an absolute minimum. Likewise, right there, we have an absolute maximum. One more thing I'll say about this before we delve back into this first example is there's a little bit of language going on here. So you could say you have a, for example, in this first one here, I could say I have a relative minimum at the point 2 comma negative 4. I could also say I have a relative minimum at x equals 2 with a value of y equals negative 4. So the minimum always is occurring at the x value, and the value is the y value. So often when we look for where the minimum is occurring at, that is the x value. If they're asking you what the minimum is, that is the y value. So just be careful when you're reading questions like that to make sure you're actually answering the question they're asking. All right, let's look back at this first example though, because I would like to kind of fully go through how we graph something like that. So let's fully graph f of x equal to, what was it there? Actually, probably, I'm going to change it up. I have a different example that's slightly different that I prefer. X cubed minus 6x squared. Let's make it a little more interesting. So when we graph something, I would say there's kind of 4 typical things we look for. The 4 things are 1, intercepts, as usual. 2, asymptotes, which this won't have any because it's a polynomial. Polynomials never have asymptotes, but we should still think about them for a second. 3, what I broadly call the first derivative stuff. So meaning where the function is increasing, decreasing, where you have a relative max, relative min, that's kind of all the first derivative stuff. And then in a similar way, the second derivative stuff, where the function's concave up, concave down, and where we have any inflection points. And that's pretty much the entirety of what we should look at when you're graphing things. There are other things you might consider, like even or odd symmetry, or whether it's periodic, but really, no, we don't really think about those things, to be honest. Like these are the 4 things you look for. And if you notice something else, great, good for you. If you don't, that's totally fine. Occasionally you might be like, oh yeah, this function is even. It's reflective about the y-axis. Oh yeah, this function's odd. It's rotationally reflective, but usually not. So let's start off with the intercepts. So y-intercept, set x equal to 0, and we're going to get f of 0 equals 0 minus 0, which is 0. Cool. By the way, if you know that one of your if you know that your y-intercept is 0, you know that one of your x-intercepts is also going to be 0 because you've got the origin as one of your intercepts. X-intercepts, set the whole thing equal to 0. Usually for the x things, like the x-intercepts and the vertical asymptotes, it's much, much better if you have factored it completely. So let's factor this and get x squared times x minus 6 to give us, equal to 0 to give us x equal to 0 and x equal to 6. So those are going to be our x-intercepts. Cool. Done with the intercepts. Asymptotes, there are none. You only get well, that's not, I shouldn't even say that. There's lots of ways you get asymptotes. Often by having a rational function or an exponential function or a logarithmic function. Those are kind of the main things I can think of off the top of my head that have either horizontal and or vertical asymptotes. First derivative stuff. So let's find the first derivative. F prime of x is going to equal 3x squared minus 12x. It's almost always going to be in your interest to factor this. I'm going to factor it as 3x times x minus 4. And the whole reason we're finding the first derivative is so we can find the critical points or the critical values. We're going to take our first derivative and set it equal to 0. Technically, you should be considering where it's either 0 or undefined, but we already know this is never going to be undefined, so we don't need to write that down. But for future examples, we might consider that. Or we should consider that or think about it at least. So here we're going to get x equal to 0 and x equal to 4. And then I think the next thing you should do is put them on a number line. So number line for your first derivative, we've got 0 and 4. You should only put the critical values on your number line. You should not include anything else. So if 0 isn't a critical value, you shouldn't put it on your number line. I know it's very tempting to want to put 0 in the middle, but don't include 0 unless it's a critical value. Okay, so then we're going to test the sign of the first derivative. So I'm just going to pick a value larger than 4, like 5, and plug it into my preferably factored form. Positive times a positive is positive. And then I'm going to do the same thing in here. Or, well, I could pick a number, plug it in, plug into positive, negative, negative. Or you could say the 4 came from this factor. That factor is raised to an odd power, so the sign's going to change. Similarly, 0 came from this factor with an odd power, sign's going to change. And then we can say, oh, if the first derivative is positive, that means our function itself is increasing. The first derivative is negative, the function is decreasing. First derivative positive, the function is increasing. And I am of the opinion that the first derivative test especially, or I should say the first derivative sign chart, is really useful for helping us draw the graph of the function. It's essentially showing you the shape. Oh yeah, the function is getting bigger, and then getting smaller, and then getting bigger again. So that's going to help us graph this the most, I think. We should still find the first derivative stuff. The second derivative stuff. But here, this is really good to have. Sure. I don't love being asked where it's increasing or decreasing because I'm like, well, there it is. It's clearly increasing from there to there and there to there and decreasing from there to there. But if you actually had to write it out, we would say it's increasing on the interval from negative infinity to 0 with a parentheses. You never include the endpoint. Union 4 to infinity. And we would say it's decreasing on the interval from 0 to 4. Should almost, I can't think of a time where you should ever have brackets on one of these intervals. For increasing or decreasing, always parentheses, never brackets. I hesitate to say never because, there's always exceptions, but I feel like this is I'm pretty sure it's a never. All right. And then we should talk about the first derivative test. So this picture here where the function is increasing, decreasing, tells us if we have a relative maximum or minimum. So at x equal to 0, the function goes from increasing to decreasing. So it was getting bigger and then stopped getting bigger and started getting smaller. So we have to have a relative maximum there, right? We got bigger and then we got smaller. There's a maximum right there, like that. So x equals 0, we have a relative maximum. Since I'm going to graph this thing and I want to include the relative extrema, I should find the y-coordinate, but I already know the y-coordinate because we already found the y-intercept by plugging in x equal to 0. So our relative maximum, and it's at the point 0, 0. We also, though, at 4, have a relative minimum. We should plug in 4 to get the y-coordinate so we can actually graph it nicely. So I plug in 4. I don't want to plug in 4 to the non-factored form. I would much rather plug in 4 to the factored x squared times x minus 6. So if x equals 4, f of 4 is going to be 4 squared times 4 minus 6 which is 16 times -2, which is -32. So my relative minimum is the point 4, -32. Now we're essentially going to do the same thing for the second derivative stuff. We're going to find the second derivative, we're going to set it equal to 0, and then we're going to find where it's positive and where it's negative. And we'll talk a little bit more about that after we do this here. So here's my first derivative again. It is x cubed minus 6. Nope, that's not the first derivative. That's before I took the derivative. Sorry. My first derivative was 3x squared minus 12x. I do prefer the unfactored form for finding the next derivative. So then the second derivative is going to be 6x minus 12. Set that equal to 0. And you can either factor out a 6 and say 6 times x minus 2 equals 0. So x equals 2. Or you could have added 12 and divided by 6. Either way. I'm going to need that. So then again, just like for the first derivative, we're going to do a number line for the second derivative. Only putting our critical value on there, nothing else. And then again, we're going to test the signs. So pick a number larger than 2, like 3, the whole thing's going to be positive. Pick a number smaller than 2, like 1, the whole thing's going to be negative. Now, when the second derivative is positive, that means the function is concave up. We'll say more about that after this example. Similarly, when the second derivative is negative, the function is concave down, like a frown. We say up like a cup, so up like a cup, down like a frown. It works. So I would say you don't really need the second derivative stuff to really accurately graph the graph, but it's helpful. It doesn't hurt. It just, you could probably get away without doing it if you were allowed to, but you probably have to do it anyway, so we'll do it. Let's graph the thing. So I'm going to plot all the points I have. Let's see, I've got the point 0, 0, great. I've got the point 6, 0. Let's say it's about there. Usually my y-axis ends up being a lot more condensed versus my x-axis. That's fine. Like if that's 6 here, I'm not going to draw it all the way down to -32 on my y-axis, like at least not with the same scale. And then, so I'm going to label that as 6, 0. And then I have, let's see, my first derivative stuff, I had a relative maximum at 0, 0, a relative minimum at 4, -32. So 4 is about right there. And then let's say it's about, I don't know, there-ish. And now what I'm really going to do is I'm going to look at my first derivative sign chart and be like, okay, it's increasing until I get to 0, decreasing until I get to 4, increasing afterwards. So it should look something like this. Looks pretty okay. I will then go and label my inflection point. Oh, I didn't find my inflection point. I was a little bit lackadaisical there. Sorry. I found the x coordinate. So, in fact, I didn't even say anything about inflection points. Sorry. So, we do have an inflection point at x equals 2 because that's where the concavity changes from either negative to positive or positive to negative. Doesn't matter which way it changes. Unlike finding a maximum or min, it matters if you go positive to negative or negative to positive. For an inflection point, it doesn't matter which way the concavity, which order the concavity changes in. So we have an inflection point at x equals 2, and the y value would be f of 2, which if we look back at our original function, it's x squared times x minus 6. So that's going to be 2 squared times 2 minus 6, which is 4 times -4, which is -16. So our inflection point's about right there. Again, it doesn't have to be perfect. And that looks like where the concavity changed, right? It kind of looks like it's concave down here, like it's opening downwards, and it's concave up here. The way I've come to like thinking about concavity is that if a function is concave down, any tangent line you draw should be above the function. So you think about it here, if I drew a tangent line above, 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 and then right about there, the tangent line stops being above and starts being below. So weirdly, an inflection point is where the tangent line goes through the function. Because then over here, all my tangent lines are below, below, below. I'll say more about that in a minute, but that's kind of how I think it's easy to kind of make sense of that when you're looking at your graph. You're like, okay, this section is concave down because all the tangent lines would be above. This example is pretty straightforward, but when you have something that looks more like, yeah, let me show you one thing here. If you had a graph, for example, and I'm just going to make up a graph real quick. Let me think for a second here. Yeah, let's do that. If you had a graph that looked like this. So let's see here. So over here, which way are we concave? Concave up or concave down? Definitely up. Until about maybe right about here. And then it looks like the concavity switches to being opening downwards. And then it kind of looks like maybe over here it switches again. Like, but I look at this part here, I'm like, it's hard for me to kind of say to myself, that's opening upwards. Like, it just doesn't feel like the right wordage to use. I think it's much more sensible to be like, oh yeah, of course. Over here, any tangent line I draw is below the function. So we're certainly concave up over here. And then from like here to there, any tangent line I draw is above. So we're concave down. And then after here, oh yeah, if I draw a tangent line, that tangent line is definitely below. So we're concave up again. To me, that just seems like an easier way to figure out what's going on as far as the concavity is concerned. So on this graph, we would have an inflection point there and there. We'd have a relative maximum right there. We'd have a relative minimum right there. Do we have an absolute maximum? No, right? Because it gets forever big over this way. Do we have an absolute minimum? We do actually. This point right here, the way I've drawn this, that is the very lowest point because I've drawn this in a way that should imply that we have a horizontal asymptote over here. So this is just getting closer and closer to zero, but here we really did hit zero. So this graph would also have an absolute minimum there. Let me just give you one more example of some food for thought. What about the function e to the x? And I'm going to say kind of disappointing. Wow, that's maybe the worst e to the x I've ever drawn. Sorry, it's still not terrible. But I just wanted to point out, e to the x kind of disappointingly has nothing. No intercept. Oh, that's not true. It has a y-intercept. Okay, it's got a y-intercept. And it has a horizontal asymptote. But it doesn't have an x-intercept. It doesn't have a relative maximum, a relative minimum, an absolute maximum, an absolute minimum, an inflection point. It's kind of lacking, right? E to the x has not a lot of interesting features. It's still a very useful and important graph, but I'll point out, like, if you tried to find the things here, you wouldn't find a lot of things. I was going to talk more about concavity. Yeah, let's talk about concavity for another moment here before we do a couple more examples. What time is it? Yeah, we'll try to get to some L'Hopital's stuff too. Okay, so I was saying before, this function, I'm going to look at f of x equal to x squared, is for sure always concave up. Just visually, you can see it. Here's what I want you to know about this, though. So if the function's concave up, and we can see that, I'm going to write it again. I know I just wrote it. I'm going to write it again. What does that mean about the derivative? Well, let's talk about it. We always go from left to right, we're thinking from left to right. If I start way over here on the left side of this derivative of this function, is my derivative very positive or very negative? Very negative, right? If I move a little bit to the right, it's still negative, but is it more negative or less negative? I know it might be kind of hard to see, but my line is a little less steep there. So I would say it's less negative. If I move a little even further right, it's less negative. And then 0. and then a little bit positive, and then a little more positive, and then very positive. So if you go from very negative to less negative to 0 to slightly positive to more positive, the whole time, were you getting smaller or getting bigger? We were very negative. We got less negative, meaning we got bigger. 0, even bigger. A little bit positive, even bigger. More positive, even bigger. So the whole time, the derivative has been increasing. The whole time, if you're concave up. Hey, wait a minute. We know something about increasing functions. If a function's increasing, what about its derivative? Let's see, look back here. Let's see here. We saw before that when the function was increasing, the derivative was positive, and vice versa. Those things are always interlinked. If the derivative is positive, the function is increasing, and vice versa. If the function is increasing, the derivative has to be positive. But that means here that if this function f prime of x is increasing, its derivative must be positive. But the derivative of the derivative is the second derivative. So that's exactly f double prime of x is positive. What I really want you to see here is that all three of the things I just wrote mean the same thing. Any one of those things means exactly the same thing as the other thing. It's just different words to describe the same thing. Kind of like with the exponential growth and decay stuff, how we talked about how like you could say something's growing exponentially, or you could say its relative growth rate is constant. Those are totally different phrases that still describe the same situation. Same idea here. And then I think we could all go the other way. If it's concave down, like f of x equal to negative x squared, then we can say, oh yeah, f of x is concave down, or now the derivative is starting off very, very positive and then getting smaller, less positive, smaller 0, smaller slightly negative, smaller very negative. So that the derivative itself is decreasing. And then that would mean that if the function f prime is decreasing, its derivative must be negative. So that's how we end up getting that, oh yeah, the second derivative is negative, the function has to be concave down because of all this. Cool. Let's graph a few more examples. Oh, there's one other thing I should do. Okay, all right. Okay. We'll graph one more example and then we'll talk about a slightly different thing as well. So where'd you go? Example. We're sticking with some easier examples to start with. Let's graph f of x equal to x to the fourth minus 4x cubed. Oh, sorry. We're going to do all the things again. Again, we know this one's not going to have any asymptotes because it's a polynomial, so we can skip the asymptotes here. But we're going to find all the things. So y-intercept, f of 0 is again 0. Not very exciting. X-intercepts, set the whole thing equal to 0. We can factor out an x cubed times x minus 4. So we end up getting either x equal to 0 or x equal to 4. Let's find the first derivative stuff. Excuse me. So let's see, take the derivative. It's going to be 4x cubed minus 12x squared. Let's factor that as 4x squared times x minus 3. Set it equal to 0. We're going to be getting critical values of x equal to 0 and x equal to 3. Number line it up. 0 here, a 3 there. looking at what's happening to the first derivative. So we're looking at this most factored form here. Pick a number larger than 3, like 4, positive, positive, the whole thing's positive, the function's increasing. Pick a number between 0 and 3, like 1, positive, negative, so the whole thing's decreasing. Pick a number like -1, positive, negative, so the whole thing's still negative, so decreasing over there. So at 3, do we have a relative maximum, a relative minimum, or neither? Definitely a minimum, right? Because we're going down and up. So we have a relative minimum at 3 comma whatever f of 3 is. Which we could find, right? F of 3. Ooh, again, I don't love the unfactored form. I'd much rather plug in 3 here and get, let's see, 3 cubed is 27 times -1, so -27. On the other hand, at 0, we have a max, min, or a neither. Definitely a neither, right? Because it's not big, it's not increasing, decreasing, or decreasing, increasing. It's both the same. So it's a neither. So we don't really write anything as far as the first derivative is concerned. Sorry, I'm always just, I suppose I should mention here where it's increasing, decreasing. I don't think you need to write this unless you're asked to. Definitely, in fact, I should say, if you're taking an exam and they ask you to graph something, you should just draw this little chart unless they specifically ask you to say where it's increasing or decreasing. Don't spend the time writing that down unless you're asked to do that. This is enough. You can read this and be like, yeah, I know where it's increasing from 3 to infinity. And this one's a little bit interesting because where is it decreasing? Negative infinity to, do I need to stop at 0 and then go from 0 to 3? Not in this case, no, because the function's completely defined on the whole interval, so we can just go straight from negative infinity to 3. But there are other examples where you do have to stop at a place because a function might be undefined there, which we'll talk about hopefully today. We'll see. Yeah. Time, always running out of time. Okay, so we've got that. Now to the second derivative stuff. So second derivative. So we're going to find f double prime. Sorry, you can't see that. Apologies. You guys tell me if you can't see something. So f double prime is going to be, let's see, here's our first derivative. So it's going to be 12x squared minus 24x. Now I would factor out a 12x. I'm left with x minus 2. So I either get x equal to 0 or x equal to 2. So plotting those on my number line. Looking at the second derivative, if I plug in a number larger than 2, like 3, positive, positive, whole thing's positive, so it's concave up. Between 0 and 2, like 1, positive, negative, so whole thing's negative, so it's concave down. Less than 0, like -1, negative, negative, so the whole thing's positive, so it's concave up. So it looks like we have how many inflection points? Show me on your fingers. How many inflection points do I have? 0, 1, or 2? Definitely 2, right? There's one there, and there's one there where the concavity changes. So you have an inflection point at 0, 0, and at 2, comma f of 2. I guess we should find f of 2, plug it back in over here. 8 times -2 is -16. And I guess for completeness' sake, if they asked you where it was concave up and concave down, we would say it's concave up on the interval from negative infinity to 0, union 2 to infinity, and concave down from 0 to 2. Okay, we've done all the things. Now we're going to graph it. So let's see, I have some points. I have 0, 0, and 1, 2, 3, 4, 0. I have a minimum at 3, comma -27. So over here at 3, I'm going to go down some ways, maybe there. And then I don't really bother trying to graph the inflection point. I just kind of label it after I've graphed the thing because it's a losing battle. So let's see. We are coming down, but we're concave up, so we have to be kind of going this way. We're going to flatten out at 0 because the derivative is 0 at 0, right? It's a critical point. We know that f prime of 0 is in fact 0. But then we're going to keep decreasing, but now we're going to be concave down. to kind of switch which way we're opening, kind of be like that. And then from 0 to 2, we're concave down, and then we kind of switch and start being concave up. Bottom out there at 3, and then come back up this way. So this is the point 3 comma negative 27. There's 4 comma 0. There's 0 comma 0. And somewhere here, it looks like it's more there, but I'm going to label it like over here, 2 negative 16. Looks decent enough, right? It's certainly concave up over here because the tangent lines are below the graph. It's concave down right here because the tangent lines are above. And it's concave up right here because the tangent lines are below. Seems legit. All right. Let's say one other thing about extrema here. So I've mentioned quite a bit about relative extrema, but I haven't really talked about absolute extrema, other than showing you on some graphs how they could have absolute extrema. But usually when we talk about absolute extrema, it's more in the context of, for this function on some predefined closed interval, find the absolute extrema. Because there's a theorem, it's called the extreme value theorem. It says, if f of x is continuous, wow, can I spell continuous? U-O-U, yeah, sure. Continuous on some closed interval a, b, then f of x must attain an absolute maximum and an absolute minimum in that interval. That's what the theorem says. What that means in practice is if you're asked to find them, here's what we do. So actually, I'm going to go back to a previous example, but change it a little bit. So let's say our function is, again, f of x equals x cubed minus 6x squared. And we want to find the absolute extrema, meaning the maximum and the minimum, of f of x on the interval from -1 to 7. Here's how we do this. To find where you have absolute extrema, they're either going to occur at the endpoints or where you have a critical value where the derivative is 0 undefined. Because, right, to have an absolute extrema, it can't be a place where the derivative isn't 0 that's not an endpoint. Because if it wasn't 0, the function would either be increasing or decreasing, and it's going to get either bigger or smaller in whatever direction you need to go. So it's got to be either, I should say, our candidates for the where are endpoints and critical points. Okay, so let's find the critical points. We already found the critical points though for this one, right? We took the derivative of this. We said, oh yeah, f prime of x is 3x squared minus 12x. We factored out a 3x, and we ended up getting x equal to 0 and x equal to 4. So our candidates for where we might find the absolute maximum and the absolute minimum are the following. At x equals 0, x equals 4, and then the endpoints, x equals -1 and x equals 7. How do we tell which one's the biggest? We plug it into the original function to see what the y value is. And the same thing for the small. So we're going to plug each of these candidates into the original function and then just see, hey, that one's the biggest, or that one's the smallest, and that's where your absolute max or absolute minimum is. So let's take a look here. So for x equals 0, f of 0 is going to be 0 minus 0, which is 0. For x equal to 4, f of 4 is going to be, I guess I like the factored form better, x squared times x minus 6. It's going to be 4 squared times 4 minus 6, which is 16 times -2, which is -32. For f of -1, we're going to get -1 squared times -1 minus 6, which is 1 times -7. And finally, for 7, f of 7 is going to be 7 squared times 7 minus 6, which is going to be 49 times 1. So then the biggest value is 49. So that means we have an absolute maximum at x equal to 7 with a value of y equal to 49. Or you could save yourself a lot of writing to say it's at 7 comma 49. Similarly, we have an absolute minimum. I'm going to write the easier way here. Absolute minimum at the point 4 comma negative 32. If we look back at our graph for this, somewhere. If I had cut this graph off from, say, -1 to +7, you can see visually, oh yeah, there's 7 comma big number. There's -1 comma not very negative number. And there's my minimum. So from here to here, just looking at that, yeah, the absolute maximum is right there. The absolute minimum is right there. So if you have a continuous function on a closed interval, it must have an absolute max and absolute min. And this is how we test for them, by finding all the critical points, all the endpoints, and plugging them all into the original function. I totally forgot about the ones you had given me over here. Sure, let's look at that one. Questions about this before we move along. This process is not very exciting. The one thing I'll warn you about for this process is, yeah, let's see what time is it. Never enough. Let me just give you one more quick example because I do think there's something worthwhile to see here. Let me think real quick here. It's all right. Sorry, I got to make it look good. -2 plus 6. Let's see. So let's say we have the function f of x equal to x cubed plus 2x squared minus 4x plus 3. And we want to find the absolute maximum / minimum on the interval from -4 to 0. Oops, sorry. So there's your function, x cubed plus 2x squared minus 4x plus 3. And you want to find the absolute maximum on this interval. So here's what we're going to do. We're going to find the critical points. So it's going to be, let's see, 3x squared plus 4x minus 4 equal to 0. This might factor, it might not. You could use the quadratic equation. I will tell you it does factor. It factors as 3x minus 2 times x plus 2 equal to 0. So our critical points here are x equal to -2 and x equal to positive 2/3. So then what do I need to check? Well, I should check my endpoints. So f of -4, f of 0, and what else? My critical points, right? F of -2 and f of 2/3? No, not f of 2/3. Why not? We're in this interval. Is 2/3 between -4 and 0? Definitely not. So sometimes people try to be a little bit tricky with these problems and make it so that one of the critical points isn't in the interval that you're actually been asked about. You don't need to check 2/3 if it's not in the interval, right? You couldn't have a maximum of 2/3 if you're asked about the function on the interval from -4 to 0. So don't get tricked by that. It's an easy thing to miss, but it's an easy thing to not miss as well. Also, 2/3 would be terrible to plug in, so we're glad we don't have to do that one. So not f of 2/3. So if we plug it, so then we have to actually plug it in. So let's see, -4 cubed is -64. 2 times 16 is 32. -4 times -4 is +16. Plus 3, that's going to be -32, -16, -13. Plugging in 0 is easy. You get 0 plus 0 plus 0 plus 3. Plugging in -2, you're going to get -8. Plus 2 times 4 is plus 8. Those cancel. -4 times -2 is plus 8. Plus 3. Cancel, cancel. We get 11. So it looks like we have an absolute minimum at the point -4 comma -13. And an absolute maximum at the point -2 comma 11. Cool. We'll look at one more graphing thing, and then we will try to say some words about L'Hopital's rule. Sorry, no, I'm moving a little bit quickly, but there's so much to say. All right, this one was asked. So here we have, we're going to consider the function f of x equal to 4 over x minus 7. We want to find out where it's increasing, decreasing, concave up, concave down. Not too terrible, but a little bit terrible because it's a quotient, a rational function. Still the same idea, though. We're going to find the first derivative. I would point out here, just because I can't help myself, that if I was thinking about this, I would think about graphing it. My y-intercept, if I plugged in 0 for x, I get 0 comma -4/7. I don't have an x-intercept. Vertical asymptote would be x equal to 7. Horizontal asymptote would be y equal to 0. Now I'm ready to do my first derivative stuff. So first derivative, bottom. I'm doing more work here than I should, but we should do it anyway. Bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So that's going to be -4 over x minus 7 squared. And if we set this equal to 0, we don't get any solutions. Let me ask you an important question. Does this function have any actual critical values? What might be a critical value? What's like the only plausible candidate for a critical value here? Lucky number 7. Technically, though, 7 isn't a true critical value. And the reason it's not a true critical value is because it's not in the domain of the original function, right? The original function, you can't plug in 7. You got a vertical asymptote there. But even though we don't have a true critical value there, it's still important to include it on our sign chart for our first derivative, because the sign of the first derivative might change there. It might not, but it might. So we're going to do that. So if I do that, let's see. 7, f prime, pick a number larger than 7, like 8. Here's what I see. The bottom's always going to be positive. The top's always going to be negative. So whether I plug in 8 or 6, the first derivative is still going to be negative, which means my function is decreasing, decreasing. Ooh, so where is it decreasing? On the interval from -infinity to not infinity, because we can't include 7, right? The function's undefined at 7. So we have to go -infinity to 7 union 7 to infinity. And we will graph this one in a minute, because I do think you all should see what it looks like. Then and it's not increasing anywhere, right? So we wouldn't even write anything about increasing. As far as the concavity, let's find the second derivative. Now, I should point out, I did too much work here. What I really should have done for this function to begin with is I should have written that f of x was equal to 4 times x minus 7 to the -1. So that then when I take the derivative, I got -4 times x minus 7 to the -2 times 1 if you're thinking about the chain rule. Much easier than trying to use the quotient rule here, I think. And then for my next derivative, again, I can not use the quotient rule and just be like, hey, power rule, chain rule. -4 times -2 is 8 times x minus 7 to the -3rd. And then yes, times 1 if you really like it. And then I would probably rewrite this as 8 over x minus 7 cubed. Again, 7 is not a true critical value, but it's still something we have to include on the number line. The only thing really. So concavity, f double prime. Pick a number larger than 7, like 8. 8 minus 7 is 1. 1 cubed is positive, so positive over positive, the whole thing is positive. And then over here on the other side, plugging something like 6. 6 minus 7 is negative, and negative 1 cubed is still negative. So this whole thing is negative over here. So it's concave down, concave up. So we have an inflection point at 7, right? Right? We have an inflection point at our vertical asymptote. We don't have an inflection point at 7. You can't have an inflection point if the function isn't defined there. Just like you can't have a critical, a max or a min if the function isn't defined there. So even though it's, you might like to be like, oh yeah. So here's what I recommend doing actually when you're doing these things, whether you're graphing or you're just finding where it's increasing, decreasing. I started off by saying, what do we have at 7? What do we have at 7? What kind of asymptote? A vertical asymptote. So I really like to just say, hey, look, there's a vertical asymptote right there. I'm just going to draw it in on all of these, so that when I'm talking about finding the max or the min or the inflection point, I know that there can't be one where there's a vertical asymptote. I think it's a really good thing to remind yourself of. Here's what this thing looks like graphically. There's not a lot of points to consider. We have a vertical asymptote at 7. We know the function's decreasing and then decreasing. So here's how it looks. It's decreasing like this, concave down, and then it's decreasing like this, concave up. It's technically decreasing on both those intervals, but we can't include 7 in the interval decreasing this. It's kind of cool. It's a good question. I like that. Yeah. So yeah. Let's switch gears a bit. I know we've talked a lot about kind of graphing things, but I do feel like I should give some 15 minutes of time today to talking about L'Hopital's rule, because L'Hopital's rule is certainly important. So L'Hopital's rule. You can't always use L'Hopital's rule. So here's an example of when you could use it. We're not going to use it just yet, but I'm going to point out that if you have the limit as x goes to infinity of 3x squared plus 5x plus 1 over 7x squared minus 2x plus 3. I think you all could tell me that this limit is equal to what fraction? 3 over 7, right? The usual kind of thing. Oh, yeah, same highest power, great. But if you just plugged in infinity for x, the top would be infinity plus infinity. The top is definitely going to infinity. The bottom is also going to infinity because the 7x squared is the biggest thing. It's bigger than the minus 2x there. So we have what we typically call to is an infinity over infinity type, which is an indeterminate form. When someone says indeterminate, you should just think, oh, it could be anything. That's what indeterminate really means, actually, right? It's not determined what it's going to be. It could actually be anything. So here's how L'Hopital's rule works. It says, well, if you have one of these indeterminate forms, it's infinity over infinity, or 0 over 0, which we'll get to in a minute, you can find the limit by taking the limit of the derivative of the top over the derivative of the bottom. And then plugging it, oh, but it's still infinity over infinity. So I'm going to do it again. Also, when I use L'Hopital's rule, I typically write an L apostrophe H above the equal sign. It's pretty standard, not required, but it's a good idea so that the person who's reading your work knows that you're using L'Hopital's rule in that step. So I do it again. The derivative of 6x plus 5 is 6. The derivative of 14x minus 2 is 14. And now you're taking the limit of a constant. And the limit of a constant is just whatever the constant is. So that's going to equal 6 over 14, which reduces to 3 over 7, just like we said it would. So I'm doing this example just to show you some evidence of the fact that, oh yeah, L'Hopital's rule works like you'd expect it to. It still gives you the answer you would get, even if you could do the limit a different way. In a similar way, I could say, what's the limit as x approaches 2 of x squared plus 5x minus 5x, sorry, plus 6 all over x squared minus 4. Well, if you plug in 2, assuming I've done things correctly here, you should get 0 over 0. Let's check. 4 minus 10 plus 6, yep, that's 0. Over 4 minus 4, yep, that's certainly a 0 over 0 type. Back in the beginning of the quarter, we would have done this limit by factoring and canceling, right? You could totally say, oh yeah, that's going to be the limit as x approaches 2. The top factors is x minus 2 times x minus 3. The bottom factors is x minus 2 times x plus 2. Cancel the x minus 2's, plug in the 2, and you get 2 minus 3 over 2 plus 2, which is negative 1/4. But since it's a 0 over 0, or infinity over infinity, those are the only types, right? These are the only times you can use L'Hopital's rule. If you have a fraction and it's either a 0 over 0 or some sort of infinity over some sort of infinity, meaning it doesn't matter if the signs on your infinities match or not. It can be positive infinity over positive infinity, or negative over negative, or negative over positive, or positive over negative. As long as it's some sort of infinity over some sort of infinity, we can use L'Hopital's rule. So here, we could also have said, well, I'm going to use L'Hopital's rule and say that's the limit as x approaches 2 of the derivative of the top, which is 2x minus 5, over the derivative of the bottom, which is 2x. And I would say every time you apply L'Hopital's rule, meaning you've still written the limit and just taken the derivative of the top and the derivative of the bottom, not the quotient rule, right? We're not using the quotient rule at all. After you apply L'Hopital's rule, you should immediately try to plug in whatever x is approaching. So I'm just going to plug in x equals 2 now and see if I get something. Oh, I do get something. I get 4 minus 5 over 4, which is exactly what I knew I was going to get, negative 1/4. So again, these are just examples that L'Hopital's rule actually does work. But these are examples where you wouldn't be required to use L'Hopital's rule because you have another method. However, there are plenty of limits that you can only evaluate using L'Hopital's rule. There isn't really another way to do them. Let's look at a few of those examples. So, example, the limit as x approaches infinity of x squared divided by e to the x. Both going to infinity, right? If you plug in infinity, infinity squared is certainly infinity, e to the infinity is also infinity. We have an indeterminate form. So we're going to use L'Hopital's rule. Now, you might have a guess as to what's going to happen here, because you might know already that e to the x gets bigger much, much faster than x squared gets big. Like if you compared e to the 1000th power with 1000 squared, e to the 1000th is like unconceivably big, whereas 1000 squared is only 1,000,000, right? So the denominator is much, much larger, which means we should be expecting that this limit's probably going to end up being 0, because the denominator is going to outpace or dominate the numerator. Well, let's check. So using L'Hopital's rule, you still have to write the limit. I should also point out we are only ever using L'Hopital's rule for limits, right? It's not something you use if you're taking a derivative. You take derivatives to use it, but you only use it when you have a limit. Specifically, a 0 over 0 or infinity over infinity. Nothing else will do. So then we have the limit as x goes to infinity of the derivative of the top over the derivative of the bottom. The bottom didn't change. The derivative of the top, the power got 1 smaller. So I think we can see where this is going if we do it again, because I should say we should plug in first. I plugged in, I checked. Oh yeah, it's still infinity over infinity. So I did it again. And then we're going to get the limit as x goes to infinity of 2 over e to the x. And now it's no longer an indeterminate form. You don't have infinity over infinity anymore. You have a constant on top divided by infinity. And a number that's not getting bigger divided by a number that's getting infinitely bigger is definitely going to 0. So this limit is 0. All right. Trying to think about what else to say here. So I should actually state L'Hopital's rule. So here's what L'Hopital's rule says. So if the limit as x approaches a of f of x over g of x is either equal to a 0 over 0 or some sort of infinity over some sort of infinity, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of the derivative of f of x over the derivative of g of x, provided it exists. So like if you start using L'Hopital's rule and eventually you get to the limit non-existing, you should have done something else in the first place. But if the limit ends up existing, you're totally safe. And it's usually not an issue. We just kind of throw that caveat in there to cover our asses. All right. So let's see. Let me grab Where'd you go? All right, I got no. Oh, there we go. There we go. So let's do another example that might have plagued us once upon a time. How about the limit as x approaches 0 of sine of 3x over 2x? Now, certainly you could do this the way we used to do it, where I talked about like the wish method. I was like, I wish I had a 3x beneath my sine of 3x. No longer needed. We can do this using L'Hopital's rule. Say it's going to be the limit as x approaches 0. I should put my little L apostrophe H here. Of the derivative of sine of 3x, which is cosine of 3x times 3, divided by the derivative of 2x, which is 2. And now if we plug in 0, we get cosine of 0 times 3 over 2. Cosine of 0 is 1. This is just 3 over 2, which is the same answer we would have gotten if we'd done it the way we used to do it. What else do I have? Oh, yeah, let's think about it. So there's lots of examples of L'Hopital's rule that we can check out. For example, the limit as x approaches infinity of the natural log of x divided by x squared. Now, even though the natural log of x graph doesn't look like it gets big very fast, it does still go to infinity, right? Here's your natural log of x graph. And it never quite flattens out. It's still getting bigger and bigger and bigger. It's just very, very, very slowly. I think I heard someone say like, if you added up like if you went over for every second of time there has been since like the beginning of time on the natural log graph, you get to a height of like 40. Because like just it takes so long to get big at all, but such is life. So here we have an infinity over infinity. So let's use L'Hopital's rule. So the derivative of the natural log of x is 1 over x. The derivative of x squared is 2x. And at this point, if we plug in infinity, we're not going to get a 0 over 0 or infinity over infinity type. The top's going to 0, the bottom's going to infinity. We could just say that that's going to be 0 because 0 divided by a big number is certainly 0. But if you wanted to, I think it's probably worthwhile to simplify this and say, well, this is really the same as the limit as x goes to infinity of 1 over x times 1 over 2x, which is 1 over 2x squared. And that's a little bit easier, but oh yeah, that's got to be 0. No other choice. Also, not surprising that so I should say more words here. When your limit ends up being 0, what you can also kind of interpret that as is the denominator outpaced the numerator. Which is not surprising, right? X squared clearly gets bigger much, much faster than the natural log of x graph. I mean, look at them. Here's x squared over here. It's definitely getting bigger way faster than the natural log graph, like without question. On the other hand, if the opposite thing happens, right? If I said like, what's the limit as x goes to infinity of the square root of x over the natural log of x? Those look like they're a little more comparable, right? Square root of x kind of has a similar-ish shape to the natural log. Not exactly the same, but like not that different. But if you take well, in fact, it's infinity over infinity. So if you use L'Hopital's rule, we're going to get that we have the limit as x goes to infinity of, okay, the square root of x, we should think of as x to the 1/2. Its derivative is 1/2 x to the negative 1/2. For natural log of x, it's 1 over x. And this is really where it's simplifying is important, because check out what happens if I don't simplify. I'm gonna do one simplification, but not all the way. So I'm gonna rewrite the top as 1 over 2 times the square root of x. And the bottom is 1 over x. Now, if you plug in infinity right now, you're gonna get a 0 over 0. Which you could say, well, technically I could use L'Hopital's rule again. And you're not wrong. You could use L'Hopital's rule again, but you shouldn't. So you should, before immediately applying L'Hopital's rule again, when you get 0 over 0, you should simplify the thing to see if you can just make it simpler. If we simplify this, look what happens. We get the limit as x goes to infinity of 1 over 2 root x times x over 1, but then x divided by the square root of x is just the square root of x, or x to the first divided by x to the 1/2 is just x to the 1/2. So we have x to the 1/2 over 2, and as x goes to infinity, the square root of x also goes to infinity. So we end up getting infinity. So what this means for us is that, okay, in this case, the numerator was the thing that grew faster. So if your limit to infinity ends up being 0, the denominator was the winner, the bigger grower, faster. If your limit to infinity ends up being infinity, the numerator was the thing that got bigger faster. And sometimes people ask you like to compare functions, like which of these functions is getting bigger? Well, we take the limit of one divided by the other and see what happens.